Alright, so today I want to go over a relatively difficult problem in Newtonian mechanics. So this is Newtonian mechanics. This is classical physics again, or general physics. General physics. And so what is the problem? So the problem is this ball is attached to this string, and the string is being pulled down. Okay, so the string is being pulled down in this direction, and the ball is traveling in this direction. Okay, and the ball has been pushed by something over here, and so it has some acceleration to it. Okay, so what I want to do here is I want to take a look at all of the forces acting on the ball, and we want to get an idea of what this angle is right here. You can sort of think of this as an angle of precession as the ball travels inwards towards this hole. Okay, so we want to understand the nature of this angle, and the acceleration of the ball is heading towards the circle as it rotates around the circle, eventually colliding in with the circle. Okay, so we might expect something. We might expect something like a tangent function going on here, because we have some asymptotic limit, or we have some limit that this angle can be before the force pulled downwards just overcomes, and the ball is just driven towards this hole without any angle. And so to do this problem, I like to set this up in an x dimension, a y dimension, and a z dimension. And we can say, so I'll write this up here. So in the x dimension, in the y dimension, and in the z dimension, I'll just write it like that. And likewise, we have this formula that Newton came up with as the sum of the forces. Sum of the forces is equal to the mass times the acceleration. And this, of course, is the sum of the forces in the x direction and the acceleration in the x direction. Likewise, we have the sum of the forces in the y direction is equal to the mass of the ball times the acceleration in the y direction. And same here, sum of the forces in the z dimension is equal to 0, because this ball is not moving up and down. There's no acceleration there. Okay, so that's equal to the mass times the acceleration in the z direction. We want to understand the nature of this angle right here. Okay, so this is 0. And what I have here, if we take a look at the x dimension here, we have F, and we have this force due to the push, so we'll just call that F. And we're going to also assume that there's friction involved on this table. So this is going to be a force due to friction. Okay. And then we have in the y direction, so in this direction we have the force due to tension. And in this direction we have the centripetal force. Again, I'm assuming that you know some of this already. Okay, we know some preliminaries on how to calculate centripetal forces and all that kind of stuff. And then we have, in this direction, we have the force due to gravity, and here we have the normal force. The normal force. So these are all the forces. Okay, and then we also have our acceleration, the acceleration in the x dimension, the acceleration in the y dimension. And we can note here that A times the sine of this angle. So this is where this angle comes into play. This angle right here times the sine of this angle, this is basic trig, is equal to the coordinate in the coordinate of the acceleration in the y direction, and similarly a sine, or not sine, we want cosine of theta is equal to the acceleration in the x direction. So we can begin to plug some things up in here where we have the sum of the forces in the x direction. So we have this force, that's in the positive direction. I'll say in my coordinate axis this is positive, and this is positive. So I will say that the force minus the force due to friction is equal to m times ax. We said ax is a cosine of theta. Okay. This z dimension we're not going to really worry about. Okay. Similarly here, the force is in the y direction. So this direction here, we have the centripetal force is my positive force. That's what I've defined it to be. Centripetal force minus the force due to tension. Force due to tension is equal to the mass times the acceleration times the sine of the angle. Okay? And I can actually move some of this around here. So what we have going on here now is we can rearrange. So we'll say that F, bring this down here a little bit, so F minus F mu equals A, and we're dividing both sides by the mass and the cosine term. So there's one formula, and then we have Fc minus Ft over m sine of theta equals A. Okay? Now these two things are equal, so we have F minus F mu over m cosine theta is equal to Fc minus Ft is m sine of theta. Okay? So now I'm going to multiply both sides by m sine of theta. And you might be thinking, okay, this is kind of weird. Their m's are going to cancel. Yes, that's true. But we also have an m in this term here. Okay, this is the normal, remember the normal force, the force due to gravity. This is the normal force. And in that term, we have an m. So the mass isn't really going away here. But what we get is, I'll do this whole thing out, m cosine of theta times m sine of theta. Okay, and that is going to equal Fc minus Ft. So we just multiplied both sides by this. Now the m's will cancel, like I said, and then we have the tangent of theta. So what we have is F, I'm going to come down here a little bit, F minus F mu times the tangent of theta is equal to Fc minus Ft. All right, so here's where that tangent was coming. So I alluded to this, to the possibility of a tangent coming up in the beginning of this practice problem. So what I want to do now is I want to take a look at isolating this tangent. and putting all of our substituting all of what we know for our forces here. Okay, so the force, again, this force is the mass times the acceleration. The mass times the acceleration, of course, in the x direction. I'll just say ma, okay, for right now. And mu mg. Okay, so because this is the mg is the normal force, and then we have the force of friction, or the coefficient of friction, times the tangent of theta equals fc minus f. Actually, what I wanted to do here is fc. We know what fc is. Fc is the mass times the velocity squared over r minus ft. So now we have all that we need so now we have all of these terms broken down into their corresponding formulas. Okay, and now we're just going to divide both sides by this. So we get that the tangent of theta is equal to all of this, so mv squared over r minus ft. And then down here, we're going to have this, because we're just dividing both sides by this term, ma minus mu mg. Okay. All right, so now we want to take a look at this right here. And what we'll find is something very interesting. So when the tangent of theta is equal to 0, that means the numerator has to be 0, right? So this has to be 0 so the tangent of theta equals 0 is 1. Excuse me there. So 0. So in order for the tangent of theta to be 0, the numerator has to be 0. Okay. mv over r minus ft. Because we know that the tangent function looks something like this. Okay. And at 0, the tangent takes a value of 0. So the numerator here has to be 0. That's what I was that's what I was meaning to say. All right. Well, mv squared over r is ft. Therefore, we subtract both sides and we divide by a negative, and we get this. And this is a force. This is the centripetal force in this case, is the force due to friction. So we would have to pull on this thing. We would have to pull on this thing, on this object down here, with a force equal to that of the centripetal force, in order for this value to be 0. And so this is a confirmation check for us. So the more interesting thing now, let's take a look at this here, is if theta is pi over 2, let's come back up here actually. If theta is pi over 2 is right here, we get this weird sort of property where it'll get closer, but it'll never touch. This is an asymptote. Okay? So let's see what happens if we set this equal to pi over 2. Okay? If we set this whole thing right here to pi over 2, let's see what conditions have to be met in order for this thing to be undefined. So we have this ma minus mu mg. Okay, So if we were to multiply both sides, let's multiply both sides by this, and then we'll factor a mass term out. So what we get is m pi over 2 times a minus mu g. Okay, so we multiplied both sides by this, then we factored an m out, and that equals just this side right here. So m v squared over r minus ft. Okay, so we're getting somewhere here. I'm going to bring this to this side and change some terms here. So we have minus m pi over 2 times a minus mu g plus mv squared over r equals ft. All right, so I'm skipping some minor steps in here, as you can see. But the point is, we're getting close to a force term in which we have something now that looks a little bit something like this. So I'll bring my cursor up here now, and we have, if we factor an m out now, we get v squared over r minus pi over 2 times a minus mu g. All right, so I factored an m out of this term and an m out of this term, and that equals our force, our ft. Okay, so force equals mass times acceleration. Force equals mass times some weird acceleration term right here. This is some weird acceleration term. And so what is this? So if A, this is interesting here. If A equals mu g, then this just becomes, where do I have it? I have it right here. This just becomes this again. Okay? So if we have if the acceleration is equal to some dampened factor of the acceleration due to gravity, then this ball is gonna have no angle of precession, right? It's just gonna get pulled inwards. Okay, this is a 90-degree angle, in other words. Okay, it's gonna be pulled inwards. There's gonna be no angle of precession. Okay, and therefore this term is going to be undefined. Okay, so this right here will give you, if you get like a question that asks, what does the acceleration have to be in order for this angle to be 90 degrees, you get this. This is it right here. Okay. And so this is a moderately hard problem in Newtonian mechanics. So we went through a lot, but my hope here is that you really, really were able to understand this, how to go about some Newtonian physics, and how to go about understanding how to perform these calculations through this example. And hopefully I didn't go too fast for you to really understand what's going on. And if you like how I do this, if you like my style of teaching, if you like how I go through example problems, and you want to request some example problems, you can go onto my Patreon page that I have linked in the description, and you can ask for some problems. I am starting this channel where I'm doing problems in chemistry, physics, basic mathematics, not basic, but a lot of intermediate to advanced stuff. You can also ask me questions on quantum. I'm going to be doing quantum playlists. I'm going to be doing general relativity playlists as well. Anything you have, any questions, example problems that you want done, just shoot them on over to me if you're a Patreon, and I will get them back and I'll get them posted as soon as I can. And I hope that you enjoyed this, and I will see you in the next one. Thank you.